Hi folks, so we've got another problem to work through. So this is a very simple stress analysis problem, which I took out from Ryder's Strength of Materials, the 3rd edition. So the question reads, a tie bar on a vertical pressing machine. So this is the pressing machine and this is the tie bar. Okay, so being told that it's 2 meters long and has a diameter of 40 millimeters. So we're being tasked to calculate the stress and the extension. The extension is more or less the same as the change in length, or in some contexts, the linear deflection. When the tie bar is being subjected to a load of 100 kilonewtons. So let's not forget that kilo represents what? 1,000. Okay, so this is equivalent to 100,000 newtons. And we've been getting information regarding the material. So we've been told that the Young's modulus, or the elastic modulus, is equal to 205 GPa, or gigapascal. We've been given some results, so we are expected to get a stress of 79.6 megapascal and an extension of 0.78 millimeters. So let's have a go working through this problem. One of the things I always instruct my students to do is always provide a visual representation of the given problem. So this is a very simple modeling diagram of the tie bar being subjected to a tensile force of 100 kilonewtons. We've got a revolved section here showing the cross section of the tie bar, which measures at 40 millimeters, and the original length is given as 2 meters. So it's always a good thing to try representing your problem diagrammatically to give you further understanding in terms of what needs to be solved.
Let's start by drawing a simple model diagram of the situation. We've got our tie bar, and it's been subjected to a force of 100 kilonewtons, as stated in the question. So the interaction between the bolts and the threads on the tie bar will cause the components to be in a state of tension. We can give some information that the bar is 2 meters long, and we've also been told that the diameter of the tie bar is 40 millimeters. Okay. We'll be trying to calculate the following. We've been trying to calculate the stress that the bar is experiencing. We've also been told to calculate the extension under the load of 100 kilonewtons. So let's proceed by calculating the stress. So the stress, sigma, is equal to the force divided by the area. Let's call that equation 1. So know the diameter. The cross-sectional area, A, is equal to pi e squared over 4. So this will be equal to pi over d times into bracket 40 squared. And this will give, bring our handy calculator, so this will be pi over 4 times 40 squared. And this gives us 1256.64 millimeters squared. So now that we've calculated the cross-section area, we can proceed to calculate the stress. So therefore, the stress, sigma, is equal to 100,000 divided by 12.64. So we put our values in our calculator, so 100,000 divided by 1,256.64, and that gives a stress of 79.58 meter squared, which is the same as 79.58 So we've calculated the stress. The next part is to calculate the extension. So we know that to calculate the extension, delta L over L is equal to epsilon. So let's follow that equation 2, where the strain is epsilon, which we can get through the ratio of the stress to the elastic modulus. So for this particular question, the elastic modulus, or the yacht modulus, is given at 205 GPa. We've calculated the stress at 79.58 MPa. Therefore, the strain is equal to 79.58 times 10 to the power of 6 divided by 205 times 10 to the power of 9. So if we box our values in our calculator, this will give us 3.882 times 10 to the power minus 4. So now that we know what the strain is, we can regularly calculate the extension. So since the strain is equal to the extension divided by the original length, this implies that the extension delta L is equal to the strain times the original length. Therefore, delta L is equal to 3.882 times 10 to the power minus 4 times 2. And this will give our value in meters. Times 2, and that will give 7.764 times 10 to the power minus 4 meters. If we multiply that by 1,000, that would give us approximately 0.7764 millimeters. Same as 0.78 millimeters. And there we have it.
Congratulations!
Alright folks, so we've worked through the problem. So this is a very quick summary of what we just worked out. So the first thing that we have to do is to calculate the cross-sectional area of the bar. As I've stated previously, it's more or less up to you whether you want to use pi r squared, but for the purposes of these lecture series and these work-alongs, I will be using the engineer's formula, which is pi over 4 times d to the power of 2, or d squared, where d is the cross-sectional diameter. As we already know, the diameter of the tie bar measures 40 millimeters. Thus, pi over 4 times 40 squared will give a value of 1,256.64 millimeters squared, or 1,256.64 millimeters squared, however you want to have that stated. Again, it's up to you. You can convert your units from millimeters into meters if you don't know how to do the conversion. But if you're going to convert this value from millimeters squared to meters squared, you need to divide the area in millimeters squared by 1,000 squared. So please take note of that. Now that we've worked out the area, we can then calculate the stress that the bar is being subjected to. So stress, represented by sigma, is equal to the applied force divided by the cross-sectional area. The applied force is given as 100 kilonewtons, which is 100 times 1,000, divided by the cross-sectional area, which we've worked out to be 1,256.64. We do the computation, and that gives a value of 76.58 Newton per millimeter squared, which is the same as 79.6 megapascal. Now that we've calculated the stress and we know what the Young's modulus is, we can then calculate the strain in the bar. So strain, represented by epsilon, is equal to sigma divided by E. Sigma is the stress, which we calculated to be 79.58. Let's not forget that is megapascal, so times 10 to the power 6, divided by the elastic modulus, which was given as 205 times 10 to the power of 9, or a billion. We do the computation, and we get 3.882 times 10 to the power minus 4. So now that we've calculated the strain, we can then calculate the extension due to the applied force. So strain is equal to the ratio of the change in length, or the linear deflection, divided by the original length. So if we transpose this equation and make the change in length the subject of this equation, then the extension, delta L, is equal to epsilon, which is the strain, times the original length, L. L was given as 2 meters, thus 3.882 times 10 to the power minus 4 times 2 gives 7.764 times 10 to the power minus 4 meters. So if we multiply this by 1,000 to change it from meters to millimeters, we get 0.7764 or 0.78 millimeters. And there we go.
All right, folks, so hopefully everything made sense to you. So any comments that you have, can you just type it down below? And hopefully you join me in the next session as we look at further examples relating to uniaxial strain. So please share and subscribe, and I'll catch you in the next section. Bye for now.